Good morning, everybody. Welcome back. I know you want to have your exam scores and all those kind of things, but that's going to happen tomorrow, right, during the exam autopsy. So come for that. You've been through it before. All shall be revealed then. Let's see. We are moving on. This is the second mountain you have to climb. Right? Like you already know how bad this last unit was. There's good news and there's bad news. It's hard. So it's the same level of difficulty as it was last time. That's the bad news. The good news is there's really only one more toolbox that we need to go over together. So far, we have done kinematics, or basically how things move, like predicting where they're going to be after a certain time and that sort of thing. And then we did dynamics, which was Newton's laws, talking about why things change their motion, what causes things to accelerate, what's the force. And then we went into energy, which, as far as I'm concerned, is an easier way to deal with all of that stuff. Your opinion may differ, and that's fine. Different brains work different ways. So we've got those three toolboxes: kinematics, Newton's laws, and energy. The fourth toolbox and the last toolbox that we're going to teach you in Physics 4A is momentum. We're going to do that today and a little bit into Thursday. Once we're done with those four toolboxes, we're going to do them all over again in chapters 10 and 11 and 12. 12 is in the next unit. But we're going to do all of those toolboxes together in the context of rotational motion and really dig deep into circles and rotational motion and curves and things like that. So that's the idea here. One more toolbox, and then we start applying all of these toolboxes more or less at the same time to different situations. Our final unit is nothing but applications of all of those toolboxes. Where we'll do something called statics. So all the civil engineers will get really excited because that's buildings and bridges. And then we'll do gravity, rocket propulsion, orbital mechanics in chapter 13, and finally fluid dynamics in chapter 14. So congratulations, you're already halfway through. You're more than halfway through in all of the toolboxes. And we have, another hard unit ahead of us. We'll get through it together. And then the fourth unit, students usually tell me that it's not as bad. This is my way of saving some time, okay? And there are just a few places that we need to cut corners in Physics 4A to make sure it all fits into 18 weeks. And this is one of those areas. So when it comes to momentum, when it comes to this chapter, if you're seeing anything about collisions in 2 dimensions, just ignore it. I mean, I could teach it to you. It's basically just use vector components and you're done. But it's one of those areas where if you are dealing with collision mechanics on an everyday basis in your chosen careers, you will get much more detail, right? And it's not really necessary here for understanding momentum. The other part that makes me kind of sad is rocket propulsion. But I'll probably do that a little bit later when we do gravity and orbital mechanics, if I have time. So. We'll see what happens. I want to try and stick as much of chapter 9 into one day as I possibly can. So let's define it and then talk about what it isn't and then get back to how to use it. So momentum. So what has more momentum? A train sitting still on the tracks or you walking next to that train? You walking, why? Yeah, because you're moving, right? Finally, we can answer. Oh, because it's moving, right? Okay, none of this tricky acceleration, mumbo jumbo, all that kind of stuff, right? Momentum, by definition, whoa, that's not a good line. Momentum, by definition, an object's mass times its motion. That's supposed to be a V right there, and I didn't draw it very well. There we go. Okay, so I know you're going to panic. Don't panic. Don't panic. What happened? right? They're back, okay? So we're gonna be a little bit tricksy here, okay, in making sure that we deal with these in a sensible way. But do realize, unlike energy, momentum is a vector. All right, so that's one thing. Second, you've got to be moving to have it, right? Now, what has more momentum, a train or a sports car? Both of them moving. Kind of depends, though, right? Like on how fast they're going. But really, a train has a lot more mass, doesn't it? So momentum is trying to capture this idea of like amount of motion. In fact, Newton, when he first wrote down his second law, he did not write it down like this at all, okay? The idea of the change in motion hadn't really yet occurred in science. And we know, like today, we know like the modern, okay, definition of acceleration is this change in velocity, right? To speed up, slow down, or turn something. Well, if we move that m, just a constant moving into this ratio right here, this derivative, well, what's mv? It's momentum, right? So when Newton originally wrote down his second law, he said, look, add up all the forces, and that's equal to a change in momentum, right? And later, it would become more formal about this change in acceleration, the change in motion of an object. So we're going right back to the heart of Newton's laws and things of that nature. But it's important to realize that there is a connection between changing the momentum of an object, its force, and interestingly here, time. And we're going to get into that. We'll get into something called the impulse in a second. All right. Other things to know about momentum, just as a foundational idea. Momentum's conserved. Now, we've run into conservation laws before. When it came to conservation of energy, right, that was a statement that said whatever energy we start with has to be the energy we end with. And then there was all this work other stuff, which tended to kind of throw you off sometimes. You weren't sure sort of what to do with that work other, but energy conservation, very strictly speaking, right? Kinetic and potential energies. We could track those kinds of things and then maybe figure out work other, we're okay. It's a little bit easier with momentum because we don't have any sort of like momentum other or anything else going on. What we do instead is we get really picky about what our system is. So we're always going to make sure that momentum is conserved. This gets a little bit weird because if you think about it, if you're driving your car along, say, a city street, okay, as long as it's moving, does it have momentum or not? Yeah, it's got mass, it's got velocity. But then you hit the brakes. And what happens to its momentum? It went away, right? Our initial and final momentum don't seem to be the same. We had momentum, and now we don't have any when we come to a stop. It seems like there, our momentum is not conserved. But we're sort of narrowly defining our system as the car. And we need to broaden the horizon just a little bit because, in fact, where did the momentum go? What was the other object that sort of absorbed the car's momentum? The earth is the answer, right? Okay. The brakes were the thing that helped to transfer the momentum. And we often don't think of the earth, right, as either moving or absorbing motion. But a lot of times, that's exactly what's going on. Now, why doesn't the earth's speed suddenly change if you slam on the brakes? It's got a lot more mass, right, than we do, okay? And no, everybody jumping at the same time on the planet is not going to make the planet weigh less or any of that kind of stuff. And the reason being, right, number one, gravity works. Number two, the mass of humanity is so small compared to the Earth's mass. I think the Earth's mass is like 5.97 times 10 to the 24. It's like kilograms. Trillion kilograms. And our human brains shut off after about 1,000. Like, we're pretty good at 1,000. Sometimes we can imagine what 1,000,000 looks like. But after that, we actually just sort of lose the ability to conceptualize how big of a number that actually is. So, yeah, I mean, jump all you like if it makes you happy. But we're not going to be affecting the Earth too much about that. Okay, so those are sort of the baselines. But what I want to do now is really look at what's going on right here. Because there's something amazing that's sitting inside of these relationships between the change of momentum, again, a final minus an initial, a change in time, and the force. So that's applied to these objects. So we're gonna broaden just this idea right here just a little bit, right? That this change in momentum over change in time. You notice I've not really talked about how this is a derivative, right? We can fix that a little bit. We can change these little d's into bigger deltas if we use just a little bit of calculus. Don't panic, you're not going to have to integrate. I want to be sure there, right? But let's massage this just a little bit. I can multiply both sides by dt. I'm going to get the force. I'm just going to stop. I'm going to drop that summation symbol, okay? And then I have my change in momentum. I just multiply both sides by dt. That's all I did, right? Moved it over to the other side. And then if I want to add up, if I want these little d's to become deltas, I can add them all up with my integrals, right? And if I assume that the force is constant, that the force isn't changing, then that means I can move it outside of my integral here. And so I'll get f integral dt equals integral change in momentum. And then what happens to these integrals is they become deltas. I'm just going to rearrange, put the change in momentum on the front side and force times delta t on the other side. And this is true if our force is constant. Now, I won't do this to you, okay? But if the force wasn't constant, what would you be forced to do to find the change in momentum? It would be back inside and we'd be integrating over whatever the force is doing, right? And so we can do that. It's just, again, I'm saving a little bit of time. And here at Fresno City College, we make the conscious decision to offload as much calculus into physics 4B as we possibly can, okay? Which is why I'm being a little bit hand-wavy here. But let's talk about what's there in that green box, okay? Because what's in that green box is called the impulse force time relationship. Impulse, okay, is defined as the change in momentum. It is whatever momentum you end up with minus whatever momentum you start with. And notice, vectors are involved. So let's take a ball, right? And we'll throw it into the wall, right? Okay? So impulse is a change in momentum. Did the ball's momentum change when it hit the wall? Well, did the mass change because it hit the wall? No, right? Careful. Did its velocity change? The direction did, right? It wasn't so much the speed, like it went in with the same speed and came back with roughly the same speed, didn't it? There was a little bit of loss. Did you catch where the loss was? Sound, right? So there was not a perfect energy exchange there, right? So, but we'll squint and say, oh yeah, no, it came back with exactly the same speed. So the only thing that changed was the direction, right, that it did. So how would we write down the impulse of that? Well, we would calculate, so we're doing the the ball into the wall, right? So ball comes in with some initial speed, right? And that speed has a direction. So we've got to be careful. We've got to define what we mean by positive and negative directions now. So we're going to call to the right positive x, right? So if we'll put numbers on it just to make you guys happy, right? Let's say it goes in at positive 10 meters per second, okay? And then it bounces off, okay? And we say that it keeps the same speed, okay? What do I have to write down for this final velocity? Good. Negative 10 meters per second. Watch out for that. The authors of physics textbooks and the people that write the problems at the end of the chapter, they try to be tricky. And they'll try to trip you up between speed and velocity, right? They'll say a ball is moving at a speed of 10 meters per second and bounces off of a wall with a speed of 10 meters per second. What do you have to do? Make sure you track the directions, right? Speed has no direction. It's just a number. Velocity, right? Velocity is the key. All right. So if we were to calculate this change in momentum, like it kind of looks like it wants to be 0, doesn't it? We have a 10, we have a negative 10, but it's not. This is not 0. Remember, impulse, the change in momentum, is the final minus 10 minus the initial, a positive 10. And here, with these positive and negative signs, I've kept the direction in place. Notice like I was drawing vector signs above things when they were symbols, but when I put the numbers in, I'm making sure that I'm using the correct signs for the directions that they're going. What's a negative 10 minus a positive 10? Negative 20. And now we need to talk about units. So notice it wasn't 0, right? It ended up being a negative 20. We'll talk units in a second. Why is the negative sign there? What is the negative sign telling us on that 20? It's got to be a direction, right? Positive and negatives hard code our direction. So the impulse was directed which way? To the left or the right? To the left. We ended up with a negative answer, and we said to the right was positive. So we ended up with a negative answer, meaning the impulse, the change in momentum, was directed to the left. Well, as I'm about to show you, changes in momentum are equal to force times changes in time. Now, the only two things that have vector directions there are the momentum, the impulse, and the force. Time doesn't have a direction. This means that both the impulse and the force share the same direction. That's the only way this equal sign can stay equal. So if our impulse was to the left, what direction was our force? It was also to the left. And is that what happens if you throw a ball into a wall from this direction? Which way will the force of the wall be on the ball? Anybody feel like singing? It'll be backwards, right? Which again makes sense, doesn't it? Okay, so this hopefully isn't anything terribly new other than maybe, and I took the hat off because I'm getting hot, but the vectors are still around. But just be mindful of your directions, okay? Really check and make sure that you are defining what you're calling positive and then sticking to that and finding out what it means. Always interrogate, right? A number. Positive number, negative number. Ask why it's positive or negative. Okay, units. What the heck are the units of momentum? Or impulse for that matter, because impulse is just the change. So if we go back to what momentum is, it's mass times, what are the units of mass? It's a kilogram, isn't it? And then what are the units of velocity? That's a meter per second, isn't it? The brackets mean units. So what are the units of momentum? A kilogram meter per second, right? Well, isn't that close to a Newton? What was a Newton? Per second squared, right? So this isn't per second squared, but it slaves really close to a Newton. So what's the name of this one, Mr. Balogh? Right? If a kilogram meter per second squared is a Newton, then what's a kilogram meter per second? Well, it doesn't have a special name. It's just a kilogram meter per second, which I think means we have a big opportunity, don't we? We could name this unit. It doesn't have a name, and it wants a name. We should propose something. Maybe Balogh? Right? It's from here on out. Can we start a trend, right? A fad, if you will, right? Calling a kilogram meter per second Balogh. What would the plural form be? Would it be Baloghs or Bolognians? Yeah, Bolognians better. Maybe we shouldn't go. A kilogram meter per second. We'll stick with that. Maybe there's reasons why they stuck with that. Okay, so units of momentum, kilogram meter per second. Units of impulse, also kilograms meters per second, because impulse is the change in momentum. I know human brains don't seem to hear that distinction, so just to be very clear, right? Momentum is mass times velocity. What's impulse? The change in that. So why is that important? And conceptually, what the heck is going on here? So if I take, I didn't bring a ceramic mug. Imagine if you had like a coffee cup, right? Ceramic mug, glass plate or something like that. Something that would shatter if you dropped it on the floor, right? And you drop your mug over the tile floor, okay? It's going to break, isn't it? In all likelihood, it's just going to shatter when it hits the floor. But now you go somewhere where there's a rug or a carpet and you drop for exactly the same height, right? You drop it over the carpet. Is it going to break? Probably not. Depends on the carpet. But we'll pretend it's like that thick, plushy stuff, right? Okay. So why is it, given exactly the same situation, right? We're going to compare apples to apples. So we got our coffee cup. Right? And we're going to drop this thing. So it's starting at a height h above the ground. What do we know about how fast the coffee cup is going to be going when it hits the floor? It's going to be square root of 2gh, right? Like conservation of energy, we can find out how fast this thing is going to be going. But whether we are on the carpet or whether we are on the tile, right? Are you with me that the speed, the final speed here is going to be exactly the same number? If we drop it exactly, is the mass any different? Does mass matter? No, it's going to accelerate, right? The cup will be going exactly the same speed. So if we do an impulse calculation here, right? If we look at the change in momentum of the cup as it strikes the floor, all of you that were like, but Mr. Balogh, what happens when it hits the ground? Remember all that? In projectile motion and everything, right? And I kept telling you, well, that's a different chapter. That chapter's now. Okay? So we're talking about when it hits the floor. Is there a change in momentum when we drop it? Yeah, we started with 0 and we gained some, right? We took it out of the gravitational field. But we're talking specifically about the collision that's happening right here, right before it strikes the floor and right after it strikes the floor, right? So what is the change in momentum on the carpet side versus the tile side? What is the impulse between the tile? What is it different or is it the same? It's the same. Okay. I walked you right into the trap. Okay. The change in momentum is the impulse. But you know something is different. What did your brain latch onto? The what? No, what is it that determines whether or not the cup breaks? I heard it. It's the force that the cup experiences. Is the force on the cup different? Tile versus carpet? Yes. How do you know? Because you read the chapter. It's good. How do you know the force is different? What happens to the cup when it drops over the tile? It breaks, it shatters, right? It experienced more force. Over the carpet, it didn't shatter, so it experienced less force. But I'm here to tell you right now, this is the difficult conceptual part. The impulse is exactly the same. Because impulse is not impact, no matter how much they sound the same, okay? Impulse is not impact. What is impulse? It's the change in momentum. Before and after, whether it's the tile or the carpet, the cup had the same mass. And it underwent the same change in velocity, right? It was moving down at some speed, right? And it went to 0, right? In both cases, the mass was the same, the change in speed was the same at the ground, we're at the tile, at the carpet. But the forces were very different. Because what else was different? If the impulse is the same, and we know the force is different, it means the time was different. How would you describe, if I asked you, why doesn't it break on the carpet? Like, just what words would you, don't think of physics, just tell me straight out, why does the cup not break over the carpet? The carpet's softer, right? There's cushioning, right? The carpet absorbed the impact. These are the kinds of words that we would use to describe what's going on, right? Cushioning, absorption, those are words that are talking about taking more time for the impact to happen. Dropping it over the tile, the change in momentum is instantaneous, right? It happens over a very, very short time scale. And so therefore, if the time, if we compare, right, we've got this force-time relationship with the change in momentum, right? I should have done that, darn it, in green, because it's the carpet. So if we do the impulse, force, time for the carpet, and we do the impulse, force, time for the tile, right? This T is bigger than this T over here, which is smaller, which means the force is going to be smaller, but this force is going to be much bigger. Come on, iPad. All right, we're going to get a bigger force, right? And impulse, force, and time is a relationship that's all about the time and the force. We'll get to an exception to that rule in a second. But I want to really kind of nail home this idea. What is impulse? It's change in momentum. Is impulse the impact? Not at all. What's the impact? It's the force. right? And that force is determined not by the impulse. I mean, numerically it is, but mostly it's determined by the amount of time that it takes for the impulse to happen, for the momentum to change. What are these? They're barrels, a special kind of barrel, right? What are these barrels doing? Okay, they're filled with water, sometimes sand, but usually water, okay? And they are put in place to ensure the safety of what? A lot of places would say, well, to ensure the protection of the people who happen to be in a car that might be running into these barrels and maybe the pole. The cynical side of me says that the barrels are there to protect the pole, because under normal operating conditions, cars should not be running into poles, right? Okay. But officer, I swear the pole jumped right out in front of me. No, I haven't had any beers. So these are there to ensure the safety of the pole and anything that might be running into the pole. How do they do it? Do the barrels control how fast the car is going? Not at all, right? So what is the only thing the barrels can really change or affect? The time. The time it takes for the momentum to change. Is a car's momentum going to change if it tries to run into that pole? Yeah, we're going to go from some velocity to no velocity, right? The barrels are there to change the time. If we increase the time, what happens to the overall force? It goes down. We can't change the impulse. The impulse is going to be whatever it's going to be. But we can change the time. Did you know that since roughly 1992 or so, every car that's ever been manufactured has come from the factory pre-broken? Some of you are like, I knew it. I knew I had a lemon. No, I'm not talking about that. I'm talking about what? Crumple zones, okay? These are parts of the car's frame that are intentionally weakened so that if the car is in an accident, what happens? It starts to deform. Now, I learned to drive in a car that was much older than me. I learned to drive, my first car was a 1972. I'm old, but I'm not that old. It's International Harvester Scout 2. Now, for those of you that don't speak car nerd language, what I was driving was effectively a tractor that looked like a Jeep. Okay. International Harvester nowadays makes big rig trucks, and they also make farm equipment. Okay. But back in the early 70s, they decided that they wanted to kind of enter the market and be a Jeep competitor. And they looked at each other, all the engineers looked at each other and said, well, what have we got? And they said, well, we have tractors. And they're like, turn that into a Jeep. And it was made in an age when like people in Detroit were given like a lump of metal and a chisel and a hammer, and they were told, carve a car out of that, right? Cars from the early 1960s and early 1970s and 80s, they were solid. Like, if I hit something, it lost. Okay? Like, my car, my Scout was fine. Okay? Little hammer, bend out the thing, my dad would never know. Right? Okay? The problem is, cars of that age, if there was an accident, even at slow speeds, 25, 30 miles an hour, there was a good chance that there would be body bags. Because the car was fine, but the occupants were not. Nowadays, you can have fairly high-speed collisions, 60 miles an hour on a freeway, things like that, right? And what you have are cars that are totaled. I mean, heck, you can total a car just by parking it nowadays, right? You bump into that little tiny concrete thing and like the airbags go off and the insurance totals your car. Like, why is it that cars are so easy to break now?
To absorb all the impact.
To make sure that we increase the time it takes to change the momentum of the occupants, right? Yeah, everything I hit lost, but I lost the most, right? Because there wasn't very much time to change my impulse. Whereas nowadays, with all these crumple zones, what's the job of an airbag? What does it do? Decreases the force, disperses the force. How does it do it? Increasing the time it takes for a body to change its momentum. Impulse is impulse because a mass at a speed is just going to be changing to zero, right? But the airbag's job is to increase the time. I apologize to anybody that's having PTSD now about an accident you may have been in. Having an airbag go off in your face is not a pleasant day. It feels like being punched. You literally have had a small explosive go off in your face. That's how the bag inflates quickly, is with a small pyrotechnic charge, okay? And the car is now filled with fine dust, so you can't breathe. You're choking on this fine dust. The dust comes from how they pack the bag. They do like a baby powder, a talcum powder in there to make, because some of these bags have to sit in a car for 10, 15, 20 years and work, right? No failure at all in the moment you need them, right? And so this powder is in there. It's gone off. It's so fast that you can't tell, right? And now you've been punched in the face by what you thought should have been a pillow and turned out to be a brick wall. And now there's dust all over the place and you can't breathe, right? And there's sound and there's screaming and there's bleeding, whatever else is going on, right? So it, however, is a lot better than the alternative. Because what's the alternative? The steering wheel or the windshield, right? Which are much bigger punches. So let's do a calculation, okay? Let's just do kind of a what if. And what I did, okay, is I took a small passenger vehicle, okay, going at slow highway speeds, okay, and it's going to collide with a wall, right? And we're just going to compare. We're going to compare with and without barrels. And I didn't have any data for this. That I didn't look too long, to be honest with you. But I just did a what if, okay? Let's say that without barrels, a car slamming into a wall comes to a stop in half a second. What I mean is, like, it takes half a second for all the pieces of the car to stop moving, okay? For it to crumple and do those things. That's probably a little long, but it was a nice round number to help me with my calculations and make the numbers go easy. And then I'm going to say, okay, if we put the safety impact barrels in place, we're going to add 1 second to that overall time, which is, again, probably an over exaggeration, but we'll run with it. You'll see the difference here, okay? So we want to find force. We are talking about an impact here. So is there impulse? Is this car going to change its momentum? Yeah, because its initial momentum is what? Well, it's mv initial, isn't it? The mass is 1,500. The velocity initial, oh dear. Okay, now if I'm going to put a number in, I got to put a positive or negative sign on it, right? So now we've got to define what we mean. So maybe we're going to visualize a little picture here. Car, okay? And if the car is initially heading this way at 25 meters per second, are we going to call that direction positive or negative? Positive? Great. Okay, so good. Plus 25. So that means I've called to the right positive x, right? So there's my initial momentum. Final momentum going to be what? 0. Why is it 0? Not moving. Okay. So what does this have to do with force? What's the relationship between momentum and force? A change in momentum is equal to a force times a time, isn't it? Integrals if we have to, but we're not going to do that. So I should be able to solve this for force by dividing both sides by the change in time. There we go. All right. So now I've got to figure out, like, for case 1 here, right? Without the barrels. So the change in momentum is going to be the same in both cases. Change in momentum is going to be final minus my initial, which I never calculated out. What is that? That's 37,500 kilogram meters per second. All right. So my change in momentum is that. So my force in case 1 is going to be my change in momentum over my time. That's going to be negative 37,500 all over, and it was half a second, something like that. Yeah. Okay. So what I got here when I calculated this was 75,000 newtons. So case 1 right there. And what's the negative sign mean, by the way? It's the direction, isn't it? So if the car is moving to the right and it hits a wall, what direction will the force be on the car? To the left, right? It's got to slow it down. Okay, so that was case number 1. Case number 2, right, where we have exactly the same change in momentum. But now we're at 1.5 seconds. Here I got 25,000 newtons, again with a minus sign because that's the direction. So how much savings did we get here? Yeah, this is 50,000 newtons, which is why I chose the numbers the way I did, was to come up with easy numbers. So that's a 50,000 newton difference. How much? 50,000 newtons. What the heck is a newton? What's a newton? A little cookie filled with figs. It's about a quarter pound. It's 0.22, I think, is the actual thing, right? So a newton is a little bit less than a pound, about a quarter of a pound. So when you do the conversion, this is about 11,000 pounds of force. Difference. You woke up this morning, somebody said, look, I'm going to give you a choice today. You're going to hit something, but you can choose to hit it or save yourself 11,000 pounds of force while hitting it. What do you choose? Depends on what my test score is, Mr. Ben. No. Dark jokes aside, right? Lowering the amount of force that an occupant of this car would experience is a good thing, right? And enables much higher survivability rates, which is why cars have crumple zones, trying to increase that time. Nowadays, you see wrecks on the side of the road, and there's car parts everywhere, and people on their cell phones calling their lawyers, right? So, which, I don't know, is that better or worse than body bags? For the record, it's much better. It's the difference between 75,000 and 25,000. Right? Is 75,000 minus 25,000 50,000? Last time I checked it was. Yeah. I'm just comparing the two cases. Yeah. Yeah. I know. I go fast sometimes. What's another case? There's a quiz coming up, so get your quiz sheets out. Another case, so there's sort of a little bit of an alternative case that can happen here. In all the cases I just talked about, the change in momentum, the impulse, was held constant. But let's take a look at a case where we don't do that, okay? So this is the case, and forgive the violent imagery here, but the case of guns, pistols versus rifles, okay? In the case of a pistol, right, the barrel is shorter. But in the case of a rifle, okay, the barrel is longer. Now, which of these two weapons has a faster muzzle velocity, a faster bullet speed? It's the rifle. The rifle can send a bullet further. A rifle gives a bullet more energy. Identical bullets, identical amounts of gunpowder in the cartridge, identical weights of the bullet itself. Those can all be the same. So, the force here is the same. The force that's being applied to the bullet depends on how much gunpowder is in the cartridge. We know that the impulse is different. For the rifle, this has a faster bullet speed than the pistol. So what was different? The time. The longer barrel of the rifle means that there's more time for the force to be applied to the bullet. And so therefore the bullet's impulse will be greater. The bullet's final muzzle velocity is going to be bigger, right? So again, you got to look and see, like, what are we holding the same? What are we keeping constant, right? One thing's usually being held constant and the other two things are changing. So different examples of the force, time, impulse relationship. If we keep force the same and change the time, we can have bigger or smaller impulses. But like we talked about before, right? We can keep the impulse the same and have different times and different forces. So this boxed equation here is the master equation that controls all of that concept and idea. Before we roll into the quiz, this isn't exactly about the quiz, but just to underscore or emphasize, people confuse collisions with impulse all the time. The impulse is not the collision. Collisions were usually concerned like, what's the force on something, right? Now, in a collision, is the impulse happening? Yes. Momentum is changing, right? But conceptually in our brains, when we think of like an impact, I'm going to run into something or something's going to strike something else, we will quantify how big that impact is by talking about the force that the object feels, right? So just kind of conceptually be careful. Impulse, what is impulse? It's change in momentum, and change, that just means change in motion, right? How big was the change in motion? All right, let's do a quiz. So before we get into doing a bunch of examples, to be real clear, right? This is our conservation of momentum statement. There's no work other term in this, and we'll get around that not having another term and dealing with the losses by being clever about how we define our systems. Like, we need to make sure we've got objects interacting, all that kind of stuff. But there are two kinds of collision out there. And in these two kinds, you'll notice that we are very narrowly defining what stays the same and what doesn't. Okay? Momentum is always conserved. And to be very clear, energy, total energy, is always conserved. But notice the difference when it comes to inelastic and elastic collisions. Specifically, kinetic energy is not conserved. Just kinetic energy. So that means like the kinetic energy before and the kinetic energy after are different in an inelastic collision. For an elastic collision, everything stays conserved. Now, the good news for us is that pretty much every collision, every interaction between objects is inelastic. There's always some kind of loss of kinetic energy. Kinetic energy is usually being turned into something that's hard for us to keep track of. And example of that would be this. That was an inelastic collision, and I know it was inelastic because I heard it. There was energy there, kinetic energy of the keys falling, that got turned into sound. That's a loss of kinetic energy. So the way you tell the difference between the two in your homework is they'll try to be very careful about the language that they use. If they don't tell you, then you assume it's inelastic. You should only be doing elastic problem-solving methods if they tell you that the equation is, or the impact, the collision is perfectly elastic, right? Or they say an elastic collision happens, right? They'll give you some thing. A lot of times they'll say a collision is perfectly inelastic. I think what they're trying to communicate there is that the objects stick together, okay? So just realize that there's differences there, and if I say, it's an inelastic collision, I know exactly what I can do. I can conserve momentum. I can conserve energy. It's just I can't conserve kinetic energy. And this only applies while the objects are colliding. Before and after, we're not talking about this. Yeah. Well, the reason there's a loud sound is because kinetic energy is being turned into vibrational energy of air molecules, which we haven't taught in vibration. That's physics 4C. Okay, so most collisions that you experience every day are inelastic. Oh, I forgot to tell you, collision in physics, when a physicist says the word collision, we are not talking about every smack together of things, okay? A collision in physics is any time two objects interact with each other. They don't necessarily have to be touching. How do things interact and not touch? Magnets, okay, is a good example. Gravity is another great example, right? Is the earth touching my keys when it falls? No, I mean, the surface eventually gets in the way, right? But gravitational, so here's a collision that takes place. As soon as I throw my keys up, the earth is colliding with my keys on the way up and the way down. And I know your brain just broke. You're like, no, Mr. Bailey, that's stupid. That's not a collision is when you catch it. Okay, fine. Collision is when I catch it. But just realize in physics, a collision is any interaction. And since the keys are being pulled on by gravity up and down, they're technically colliding. So elastic collision calculations are used when we do gravitational slingshots. When we use space probes, and to get them to Jupiter, instead of sending them directly to Jupiter, we might send them towards the sun first. Get the sun to slingshot that probe and get it going much faster so it can get to Jupiter sooner, even if it takes a longer distance. Those kinds of because we don't want the probe to collide with the sun literally, but it is in a collision mode in that it's exchanging momentum and so on and so forth. The other thing, and this looks like a scary diagram, but it's not, okay? What I'm trying to outline for you here is that specifically in this chapter, in every physics textbook, they have to make it harder than it really is. The new things that I've taught you about impulse and momentum and force and time, that's all taking place in the moment of interaction between objects. What happens before that interaction can be any one of the toolboxes. And what happens after can be any one of the toolboxes, which is why I tend to think whenever two objects are colliding or interacting with each other and I'm worried about what's going to happen in that interaction, I tend to think of it as a sandwich. But physicists use food analogies for just about everything because I think we're just perpetually hungry. But this is a sandwich, right? You've got the middle of the sandwich and then you got the two pieces of bread, okay? When you problem solve, realize that in a homework problem, this new stuff is just one part of a bigger sandwich. And the pieces of bread, you might have to reach into a different toolbox to do a solution. I'm going to model this for you with some examples, okay? But just realize that I'm going to be using conservation of energy and kinematics and Newton's law, whatever I need to use, say, to figure out how fast something is going before it collides. That's not chapter 9. That's something else. That's chapters 1 through 8, okay? Then in chapter 9, we do the collision, and then we might use something else afterwards to figure out what happens afterwards. So just so you kind of have that mental model in place. And what I tend to do is I tend to start in the middle. I go straight for the middle of the sandwich, and then I figure out the pieces of bread as I go. So let's do an example here where we will take an ancient technology and determine just how did they figure out how fast cannons could shoot cannonballs and what the range of cannons were and all that kind of stuff. In an age when there was no radar or sonar to be able to measure the speed of projectiles as they move. They did it with something called a ballistic pendulum. This literally was a device that caught cannonballs. You lined up, you put one cannon. So right here is the cannon that they are testing. Okay, they're going to shoot that one. But this thing right here is going to catch it. So you see how it's like lined up right face to face, right? So this cannon's going to shoot, it's going to roll backwards, right? And this one's going to catch the cannonball, and as it catches the cannonball, it's going to swing up on it's mounted on these pendulum arms right here, okay? So we are going to figure out how it was that our ancestors figured out this stuff, right? How did they figure out how fast cannonballs could go and therefore how far they could shoot and all that kind of stuff? Again, I apologize for the violent imagery of this chapter. I've tried to figure out over the years ways to talk about momentum without mentioning guns, but it just doesn't work. If you come up with other analogies, let me know. Okay, so what do we got? We've got a cannonball, right? First step in solving any problem. What do? Visualize, right? I don't care if you are doing physics or chemistry or trying to pay your taxes or whatever it is you're doing. Sit down, you don't visualize your taxes. Don't do that, it's depressing. Okay, so we've got cannonball, right? That's moving at some initial speed. Annoyingly, the problem doesn't have any numbers in it. I'm rejoicing and you guys are dying. It's okay. Okay? And so sometimes you need like a before, during, and after picture. You almost have to become like an amateur animator here, right? Okay? So during, the ball like embeds itself in the, right? It's come in and it's embedded itself inside of the catcher. And then after that, the ball together with the catcher are going to swing up through a height h, right? It's gonna go that high from where it started. Our goal is to find that initial velocity, right? What do we know? What are we given? We know the height h, okay? We know the mass of the ball, and we know the mass of the catcher. Okay, these are all the things that we know, and we're looking for that. That's what we want. So I've kind of made a little bit of a list. I've drawn a picture. The next thing I do is I strategize, and this is where I start in the middle of the sandwich. I'm going to go straight for my middle part right here, and I'm going to start there. I'm going to end up with some things I don't know. And that's going to lead me to whichever piece of bread I have to get to figure it out. But I'm going to start right here in the middle portion, right? There's three different sort of phases right here, right? So in this middle portion, this is the new chapter 9 stuff that I've been teaching you about momentum. But here I'm going to teach you about conservation of momentum. I need to write down the total momentum of my system before and after. My system should consist of at least two things, right? There's a collision taking place. And in order for forces to exist, there have to be two objects interacting with each other. So at a minimum, what two objects do we have in this problem that are interacting? The ball and the catcher, right? Those two things. So that means that initially, and I don't always spell this out in such detail, but I'll do it the first time here. I'll have the mass of the ball, velocity ball initial, plus the mass of the catcher, velocity catcher initial. That's the total momentum of my system, right? Before the collision takes place. And then after the collision takes place, like instantly before and instantly after, are these two things separate? What's happened in this case? Are they stuck together or are they still separate things? They're stuck together, right? The catcher is named because it's supposed to do what? Catch the ball, right? So I could write this as mass of the ball plus mass of the catcher, right? The ball has embedded itself in the catcher. The catcher's caught the ball. They're acting as a single mass together, right? Times however fast this thing is going, right? I'll call it V final maybe, right? So I could write it that way, but notice if I kept it separate, mass of ball, V ball final plus mass of catcher, V catcher final. If they're stuck together, what has to be true? They have the same final velocities, don't they? So if this velocity is the same velocity, could I factor it out? And if I do that, I get the same thing, don't I? So whichever way you want to think about it, you can think of them as separate things or you can think of them as a compound object. It doesn't matter, you get the same thing because their velocities will be the same if they're stuck together. If they're not stuck together, because I think I gave you a problem where a bullet gets shot through a piece of wood. If the bullet goes through the wood, can you say that they're stuck together and they're the same object? No. Okay, so I'm looking at this thing, right? And I'm trying to figure out what I know, what I don't know, what I need to find. Okay, so I know the masses, right? Where's my green? Right there. So I know that mass, and I know that. That's good. Okay. Do I know the velocity of the bullet initial? The ball, rather. No. But that's okay. This is what I want to find, right? That's what I'm after. So it's okay for it to be unknown. Do I know the velocity of the catcher initially? It's 0, right? It's not moving. Which is sometimes why I just won't even write that term, right? Sometimes if I'm writing my initials, if I know something's not moving, I don't give it a momentum. All right. And do I know the final velocity that the catcher and the ball are moving? It's not 0. Nope. Don't know that one, right? So I've got a case here where I've got one equation with two unknowns, which is impossible to do anything with. So what I need to do is I have to go find what this V final is. And this is where I reach for a piece of bread, meaning that I've set up the conservation of momentum part, the new chapter 9 part. But everything else is totally up for grabs as to how I go about finding this thing. Okay? So let's look at the piece of bread that's sitting here in the after portion. Okay? In the after portion, I could use, so I need to find out, because the V final for the during portion could be like a V initial for the after portion, right? It's going to have that speed down here at the bottom, and then it's going to swing up to a maximum height. What's its speed going to be at maximum height? 0, okay? And I know that it changes a height h. What kind of problem does this sound like? Kinematics? Okay, could be kinematics, only you've got an arc that it's moving through. Yeah, I'd go for energy, because we don't worry about the acceleration. Don't know anything about it, don't know time, so this is a conservation of energy problem, okay? Because I really don't want to do a portion of an arc and circular motion in kinematics. All right, that's next chapter. So for this after portion, this is a different piece of bread. I'm going to set up a different kind of problem. Work other plus energy initially equals energy final. This is the initial, this is the final, this is 0. Initially, there's no work other, by the way. There's no friction or anything else going on in this section. Initially, it's going to have 1/2 mv squared. And then the final, it's going to have mgh. I'm going quickly here because we've done energy already, but are we good? The ball and catcher together, do you agree that they have kinetic energy to begin with? Sure, it's moving, right? Do they have any kinetic energy when it's done? No, all the kinetic energy gets turned into what kind of energy? Gravitational potential energy. There's no springs here. This is all I've got. The masses cancel, and the velocity is going to be the square root of 2gh. Whatever vertical height that pendulum swings through, h, multiply by 2, make sure you know what planet you're on, take the square root, you're going to know how fast it was going to get to that height. Yeah? Yep. Gets to a maximum height. Was there a question back there? Well, it's the speed that this thing had initially right here. But what is that initial speed? It's exactly the same final speed we had right after the collision. This final speed leads, this final speed leads into this section, right? Yeah. Yep. It's like 3 problems in 1. Isn't that nice? So what have I got left here? I've got mass of ball, velocity ball initial, equals mass of ball plus mass of catcher times the square root of 2gh. And I know h, so now I've got everything, right? The velocity ball, and we can just solve for the speed. We can drop the vector signs here because positive or negative, we really don't care what it's going to be. We just want to know the number. Over mass of ball times square root of 2gh. And that formula right there is called the ballistic pendulum formula. Used to be how we found the speed of ballistics. If you didn't catch the ball, then you'd have to be able to know something about how fast it was going after the bullet interacted, and that was a little bit harder. Nowadays, we just use radar. We use light pulses in something called a chronometer that is able to measure speed of projectile shot through the thing. All right, so on Thursday, I'm going to finish chapter 9. I've got like 2 or 3 more examples to do, and then I'm going to get started on chapter 10, just so you understand the pacing of where we are going. I will see you tomorrow for the exam autopsy.